The surprising truth about closed-loop industry is that it rarely means zero waste. It mostly means better coordination, better measurement, and smarter design. So losses are smaller and value stays high. Start with a strict definition, because the words get abused. A true material closed loop means taking end-of-life materials, residues, or components and turning them back into equivalent quality feedstocks. Not lower grade, not mixed filler. Equivalent quality, good enough to substitute for virgin material in the same application. That strict bar runs into 4 stubborn enemies. Contamination, because real products pick up dirt, additives, and unknown chemistry. Dispersion, because materials scatter across households, cities, and global supply chains. Degradation, because heat, stress, corrosion, and sunlight change properties over time. And reverse logistics, because getting things back, sorted, and verified is an operations problem, not a slogan. As of 2026, most closed-loop programs are partial loop closure. Collection, sorting, some recycling, some remanufacture, and selective reuse. Full same-grade cycling is real, but material-specific and often limited to controlled streams. Metals are still the best bet for repeated recovery at high value. Many alloys can be reprocessed if you manage sorting, chemistry control, and dilution. If you do not, you can melt value as quickly as you melt the metal. Mix the wrong alloying elements and you get a downgrade that no marketing language can reverse. Plastics, textiles, and composites face steeper penalties. Their properties depend on polymer type, additives, fillers, and thermal history. Separation is hard, and contamination is often invisible until failure. A major finding from comparative analysis in 2022 is blunt. There is no universally superior closed-loop recycling pathway across common plastics. Performance is polymer-specific and scenario-dependent, including cost assumptions and environmental boundaries. That leads to the first strategic insight. Circularity is not a single technology decision. It is a routing problem. Which polymer goes to mechanical recycling, which to chemical routes, which becomes additive manufacturing feedstock, which is burned for energy recovery, and which is simply not worth circulating. If you treat it as one procurement checkbox, you will fund the wrong plants and lock in the wrong infrastructure. Now shift to electronics, where the constraint is often not chemistry, but system design. Work in 2022 documented closed-loop supply chains in electronics as strategic operations problems. Reverse logistics, spare parts, product architecture, and the value retention decision, early, before the product exists. Should value be preserved through repair, modular upgrade, component reuse, remanufacture, or only at the end as material recycling? Each choice changes warranty policy, inventory strategy, and the economics of take-back. A second insight follows. The binding constraint is often operations design, not the recycling reactor. If a device is glued, laminated, shredded by default, and shipped anonymously into commodity waste streams, then no downstream sorting miracle will recreate high-purity inputs at scale. Additive manufacturing fits into this story in a counterintuitive way. It can support local circular manufacturing because some recycled polymers can be reprocessed and printed near the point of use. But the limiting variables are not just printer capability. They are feedstock history, thermal degradation, contamination control, and property qualification. In other words, quality systems. Without records and testing, recycled polymer becomes a risk premium, not a cost saver. Composites are the frontier stress test for circularity, and wind turbine blades are a vivid example. A 2025 analysis highlighted why same-grade closure is hard here. Composite heterogeneity, logistics, scale, and process selectivity dominate feasibility. You cannot easily separate fibers, resins, coatings, and structural variations, especially after decades in harsh environments. That creates a time bomb of future waste cohorts, because many long-lived assets built now will retire after 2040. Closed-loop mining adds another twist. In mining and metallurgy, closed-loop does not mean no waste. It means integrated recovery, process coupling, waste stream valorization, and traceability across extraction, processing, use, and recovery. Work formalized in 2020 and restated again in 2024 frames mining as part of a feedback system, not a one-way input sector. Tailings valorization, process water recirculation, and byproduct capture can reduce waste intensity. Yet geology and thermodynamics still impose limits. Depletion is real, and some losses are irreducible. So what actually moves the needle in the near term? 3 things repeated across sectors. First, purity, sorting, and pre-processing capacity, because contamination is the tax that kills same-grade recovery. Second, qualification and standards, because industrial buyers need variance bans, test methods, and clear recycled feedstock grades.